Sophie, could you share again? There we go.
Yep,
Oh,
sorry.
perfect.
Okay, cool.
That's good. I don't know how to get rid of a lot of things. Okay. Thanks. Now we have Sophie Libkind with with additive invariants of open Petri nets.
Thanks, David. Yeah, so I'm really excited to be here virtually today. I'm sorry I can't be there in person. So I'm excited to present this work about additive invariants of open Petri nets. That's work done with Ben Bumpus, Jordi Lopez Garcia, Leila Sorkati, and Sam Tenka. And like James's first presentation this morning, this work was begun at the AMS's MRC on applied category theory last summer. And so I'd also love to thank the organizers and also our mentor, John Baez, who conjectured a lot of the results that I'll be presenting today. So to get started, let's just start with the category of open Petri nets. It's sort of a staple of the applied category theory literature, but let's make sure we're all on the same page. So the category of open Petri nets has as objects finite sets, and its morphisms are decorated cospans. So here we have the underlying cospan and also the decorating Petri net. So if you haven't seen Petri nets before, here's an example. It has a set of species. So here we have 4 species, A, B, C, and D. And that set of species is actually the apex of the underlying cospan. And it also has a set of transitions. Here we have a single transition alpha. And that transition has sort of a source multiset of species and a target multiset of species. So here alpha takes in an A and a B and produces a C and a D. You could think of a Petri net as a way of sort of moving tokens around or in a chemical reaction network, turning some chemicals into other ones. And so this is how we draw a Petri net, and the way we draw an open Petri net is to also include the underlying cospan. So I have my underlying cospan hidden here. Here, here's the sort of left leg of the underlying cospan. X is 3, and it's pointing to the species A, and then twice to the species B. And then here's the right-hand leg. And the idea is this openness says that A and B are sort of available for sharing or being connected to other species in a composite. And this figure is taken from the original paper on the category of open Petri nets by Baez and Pollard called a categorical framework for reaction networks or something like that. So let's see how composition works in this category of open Petri nets. So here we have the open Petri net we just saw, and then another one, which is with a single transition beta that takes in a species E and produces a species F. And the way composition is going to work is we're going to identify all of the species that are connected by the legs of the underlying cospans. So here we're going to identify C with the species E, and we're also going to identify D with E. So then in our composite, those 3 species just become a single species, which we'll call C. And now alpha produces 2 copies of C, and beta takes in a single copy of C. And again, this figure is taken from that Baez and Pollard paper. Open Petri net is also a symmetric monoidal category where the monoidal product is given just by sort of stacking 2 Petri nets on top of each other. So one thing that is really, there we go, useful so you can build these really large Petri nets. And in fact, Petri nets in the wild can be really enormous with like thousands of transitions and species. And the great thing about this category of open Petri nets is instead of thinking about or coding up just this entire enormous Petri net, you can do it compositionally. So build your little building blocks and then compose them together. And once we have that structure, we want something like a compositional semantics. So the idea is a way of interpreting these open Petri nets that agrees with the composition. So if I say analyze 2 Petri nets and then glue the analyses together, that should be the same as analyzing just the whole system on its own. So a compositional semantics for open Petri nets is just going to be a symmetric monoidal functor out of open Petri. And the classic example is this law of mass action, which takes an open Petri net and maps it to an open dynamical system, which is a decorated cospan category. This is the decorated cospan category where the decoration is an ordinary differential equation. So once you've turned your Petri net, maybe your giant, here we have sort of a Petri net representing a giant Loc de Volterra model, into a dynamical system, you might want to plot it. And here we can see sort of the different species, their populations rising and falling over time. Now, a project that you might have is to, and in fact, a project in our MRC group, it led in sort of a different subgroup, was to take sort of these atomic open Petri nets and compose them to build these really giant networks and to ask the question sort of, are they biologically relevant? Suppose we're trying to build these like chemically or biologically relevant networks. And from something like the ordinary differential equation, it can be really hard to tell, like there's no, if there's 7 peaks, then it's biologically relevant or something like that. So the project for our subgroup was to sort of think about a simpler semantics. So here we're going to be studying symmetric monoidal functors from the category of open Petri nets into the single object category induced by the monoid of natural numbers. So here composition and the monoidal product in this category are both given by plus. And we'll call such thing additive invariants. And the idea is this is a much more simple compositional semantics than the law of mass action, because here we're just getting a number for every open Petri net as opposed to a whole differential equation. And the other idea is that these additive invariants can be used to represent and verify constraints. So you might have something like a network is biologically relevant if this additive invariant applied to it is always less than 100, as an example. And then also because it's compositional, you could use these features to build up biologically relevant networks. For example, if an invariant always has to be 0 for a network to be biologically relevant, that sort of thing is compositional. So the outline of my talk today is we're going to start with classifying all of the additive invariants for the category of open Petri nets. And along the way, we're actually going to use a decomposition theorem. So a way of taking an open Petri net and breaking it apart into some really simple building blocks. And because the category of open Petri nets is so widely spread sort of in the applied category theory literature, I think these decomposition lemmas are actually of independent interest. And then as a part 2, we're going to do the same thing, classify the additive invariants and look at decompositions for this category of open Petri nets where the legs of the underlying cospan are monic, and we call those MOPE nets, so the category of MOPE nets. We'll get to that in part 2. All right, so to get started, we're going to start by thinking about these. I said when we decompose a Petri net, we're going to do that into these little building blocks. So here I'm going to share with you our building blocks. So for every pair of natural numbers m and n, we're going to let p sub n, mn, be the Petri net with a single transition that has m distinct input species and n distinct output species. So here's our example of p21. It has a single transition. It has 2 distinct input species and 1 distinct output species. And then we can turn that into an canonical open Petri net. So again, for m and n natural numbers, we're going to think about the canonical open Petri net, which is decorated by that p sub mn and whose underlying cospan is the identity. So these are our building blocks for our decomposition. So to move on to this decomposition lemma, for any open Petri net p with n transitions, it can be factored as follows. So it's going to be the composite of q and q prime, and these are going to be transitionless open Petri nets with g0 through gn. G0 is special, it's transitionless, and its underlying cospan is the identity. So in fact, G0 is an identity morphism in open Petri nets. And the G1 through Gn is each isomorphic to those canonical open Petri nets P sub Mn. So let's take a look at an example. So over here, we're going to have our Petri net P, and here's our decomposition of it. So let's start with the G0 through Gn. So G0 is our top one here. And it's basically composed of all of the species in P, which are not connected to any transition. So here, E is the only species that's not connected to any transition, and it makes up our G sub 0. Now we have a G sub 1 through G sub n for each of our transitions. So here's G sub 1, it corresponds to the transition alpha. Alpha here has a single input and 2 outputs. So we're going to use that P sub 1, 2 as our G sub 1. G sub 2 corresponds to beta. Beta has 1 input, 1 output. So G sub 2 is going to be P sub 1, 1, 1 input, 1 output. And lastly, gamma also actually has 1 input and 2 outputs. And so it's also going to be given by that P sub 1, 2. So notice that these are actually isomorphic, even though alpha and gamma look a little bit different because gamma takes D as a catalyst. It's both produced and consumed by gamma. And then Q and Q prime, their roles are sort of to take all of these Petri nets and glue the appropriate species together. So for example, C is really showing up in all three of these open Petri nets. And this leg of Q prime is going to glue them all together. And so that's how decomposition works. This is how we can decompose an open Petri net into these canonical factors. All right, so now we can move on to our theorem that will classify all of the additive invariants of open Petri nets. And it sort of has two parts. The first part is to give you a class of additive invariants, and the second part is to show that any additive invariant is a linear combination of these. So for any pair of natural numbers m and n, there is an additive invariant, which we'll call f sub mn, which essentially counts the number of transitions with m input arcs and n output arcs. So if we take a look at example, we have our Petri net from before, and we see that F12 is going to be 2 because both alpha and gamma both take one species and produce two species. Whereas F11 is going to be 1 because beta is the only transition that takes one species and produces a species. And for all other pairs of natural numbers m and n, f of that will be 0. So the second part of our theorem says that actually these form a basis. So if f is any additive invariant, then f is going to be the linear combination of those building blocks f sub mn. And the coefficients are going to be given by applying f to those canonical open Petri nets p sub mn. And just to give you a little bit of a taste of the proof, let me pull out our example decomposition here. So if I take a Petri net P and then decompose it the way we talked about in the lemma, and then I apply F to it, because F is additive, that's the same as applying F to all of the factors, the Q prime, the G0, G1, G2, G3, and then adding the results together. There's another lemma that says any additive invariant of open Petri nets applied to a transitionless open Petri net is actually 0. So that means F applied to the Q prime, and the G0 go away. And we're just left with the sum of F applied to these G1 through Gn, which are isomorphic to the canonical open Petri nets P m sub n. And so that's sort of, from there, it's pretty straightforward how to finish the proof. So now we've really classified all of the invariants of open Petri nets. So the next step is to do sort of the same thing, but instead of for open Petri nets, for this category of mope nets. So we define a mope net to be an open Petri net whose underlying cospan has monic legs. So it's a wide subcategory of open Petri. And the reason you might be interested in this category is because the composition of mope nets actually preserves the relationship between transition and its input and output species. So here's the example of composition that we gave from open Petri nets. And notice that it does this thing. Alpha has these two distinct output species, but after the composition, it becomes a single output species. So before alpha was producing two separate things, now it's producing two of the same things. This is the sort of thing that cannot happen when you're composing mope nets. Because of this requirement that the underlying cospan has monic legs, the relationship between any transition and its input and output species is preserved. One thing that I think this is useful to think about is a catalyst. So a catalyst is something where the transition will both consume and produce it, one of it, can't be created in composition. Catalysts sort of only exist if they exist in the factors. All right, so we're going to follow sort of the same strategy. Let's start with our decomposition lemma. So for an open Petri net P with n transitions, we can factor it as the following composite: Q and Q prime, which again are transitionless open Petri nets, with G1 through Gn. And these are going to be open Petri nets with a single transition and whose underlying cospan is the identity. So let's take a look at an example. Oh no, sorry, before the example. So the reason this is actually true of all open Petri nets, but the reason it's relevant for this category of monic Petri nets or mope nets is that if P is a mope net, then so are Q and Q prime. So that means that if P is a mope net, this gives a decomposition into mope nets because of course G1 through Gn, since their underlying cospan is the identity, they're automatically mope nets. All right, so now let's do an example. So here we have an open Petri net P, and here's its decomposition according to this lemma. So let's start with G1 through G3 here. So the idea is G1, G2, and G3 all have all the same species as P, so A, B, C, D, and E. And then each one is going to just sort of take one transition and ignore the rest. So G1 has alpha, alpha takes A and B and produces a C. Oops. I think this arrow is going the wrong way, sorry. Beta G2 has beta ignoring the rest, and G3 has gamma ignoring the rest. And then the role of Q and Q prime is really, it's the identity on one side, and it's just to echo the legs of P to get the correct legs of the underlying cospan. So the decomposition here is pretty straightforward. So just like we had those building blocks P sub mn in the case of open Petri nets, here we're going to have a larger class of building blocks in the case of monic open or MOPE nets. Again, because you can't sort of create things like catalysts in the category of MOPE nets. So here are building blocks. For beta, a multiset in pairs of natural numbers excluding 0, 0, we're going to define and actually find these definitions way easier through example. So consider this multiset of pairs of natural numbers. It's going to define the Petri net with a single transition, and then each element of the multiset is going to define a different species and its relationship to that transition. So here, this defines a species, which is once an input and once an output to the transition, so a catalyst. Here it is. Then we have another catalyst, a species that's once an input and once an output. Here we have a species here that's twice an input to the transition. And here we have a species that's once an output to the transition. So that gives us, so every beta will define a Petri net, and we can turn that into a canonical open Petri net P sub beta by having the underlying cospan be the identity and then decorating it with that Petri net P sub beta. Now, if a transition has this particular relationship to its species, we'll call it a transition with type beta. And so you can go through any Petri net and sort of write down what is the type of each transition. So now we're ready for our theorem that will classify all the invariants of additive invariants of MOPE nets. And it follows the same structure. First, we're going to introduce a bunch of additive invariants, and then we're going to show that any additive invariant is in fact a linear combination of these. So if beta is a multiset of pairs of natural numbers, again, excluding 0, 0, there is an additive invariant, which we'll call F sub beta, that counts the number of transitions with type beta. So this is an example. You could, for instance, have an additive invariant that counts the number of transitions that have a catalyst with one input, with one other, a catalyst that turns one species into another species is a type of thing that would be an additive invariant of MOPE nets. Now, in the category of open Petri nets, we had this feature that any additive invariant of it was 0 on transitionless open Petri nets, but that's actually not true in this category of MOPE nets. So we're going to need some additive invariants that capture what goes on, or sort of capture information about the underlying cospan. So it's a little bit, so for two non-decreasing sequences of natural numbers, A and Z, satisfying this property, so n times a1 plus z1 is going to equal an plus zn. There is an additive invariant, which we'll call f of az, which is defined as follows. So f of az applied to this open Petri net, it's going to ignore the Petri net P and sort of just depend on this underlying cospan, and it'll be defined by a of s minus a of x plus z of s minus z of y. And so here we have our building blocks for all of the additive invariants of MOPE nets. All right, so the last part of the theorem says, right, if F is an additive invariant, then it is a linear combination of the additive invariants introduced on the previous page. So F is going to be F of AZ, where that sequence A is going to be defined by F applied to this, what we call a boundary net. So it's an open Petri net where the decorating Petri net is transitionless. And the right leg of the cospan is the identity, and the left leg of the cospan is the unique thing out of 0. Zn is sort of the opposite. It's F applied to this open Petri net, where the underlying cospan is the identity on the left-hand side, and the decoration is transitionless. So that gives us our FAZ, sort of what is F doing on transitionless open Petri nets. And then the other part is sort of what is F doing on those Petri nets with transitions. So it's going to be the linear combination of F sub betas, where the coefficients are given by applying F to those canonical open Petri nets, P sub beta. Great, so that's about it. We've introduced, there's been a lot in here. So we introduced 2 decomposition lemmas for open Petri nets, and also use those to prove a classification theorem, or classify all of the add invariants, both for open Petri nets and for these MOPE nets, open Petri nets where the legs are monic. So thank you so much, and you can check out the full paper on arXiv.
Wonderful. Okay, we have a lot of questions. Let's go through.
Great talk, Sophie. Thanks.
Thanks.
I had a question about there's like multiple ways of formulating Petri nets that are all slightly different.
Mhm.
How robust is this to the different formulations? Like would these additive invariants hold for like whole grain or
That's a great question.
like directed hypergraph,
Yeah, like I'm thinking
fuzzy
about whole
graph?
grain right now, and like, right, the difference between whole grain and these is it gives sort of an identity to the input and output arcs. That's a great, for some reason my gut says it's the same because my gut says they're the same, but I don't know why. Something about, I'm not sure. I like, my guess is it's something about sorry, great question, James. I don't know. My guess is it's the same.
David, do you want the cue?
My question is kind of similar.
Oh, okay.
It's kind of like you've got these two classification theorems which make use of this linear structure, and they have a similar flavor. And kind of related to what James was asking about, it seems like maybe you have, or there exists a sort of general theory of classification theorems for like decorated co-span kinds of constructions.
Mhm.
Do you have an inkling of such a theory, or are the proofs very different? I mean, yeah.
No, but definitely how we don't, but definitely how we were conceptualizing this work was as like a stepping stone to get to other types of additive invariants, either for other decorated cospan categories, as you say, or even more complex ones for open Petri nets. So instead of starting on the side of like differential equations and making them simpler, start with the simplest things we can think of and then build upwards.
Yeah, it just sounds like there's kind of something abstract lurking there.
Yeah.
Hey, Sophie, thanks. What role was the natural numbers playing here? Like, could I replace that with a different monoid, and how much would work, or the natural numbers as a target of these invariants?
Yeah, so it turned out that the natural numbers, for example, as opposed to Z, played an important role. The fact that they were non-negative allowed us to do some manipulations in some of the lemmas. Something that we did think about for a while was to have the monodal product be something other than plus, so something like, yeah. But
what about the non-negative rationals or something?
The non-negative rationals.
Like, would your decomposition lemmas still help you with other monoids, or are the integers really the only?
I'm not.
Well, the decomposition is fixed, right? Like, you can decompose it.
Yeah. Maybe I'm asking a dumb question. Apparently, I just wondered about the target of this monodal functor.
I think it should work if you go into non-negative rationals, but
at least the decompositions are useful.
Yeah. The decomposition seemed useful across the board, and I was wondering whether you needed something about the naturals as opposed to, say, the non-negative rationals or something to.
Yeah, I don't think anything. My guess is the non-negative definitely was important. I don't remember anything specific about the naturals, so the non-negative rational seems like it would probably work.
Cool, thanks.
Yeah, so you have a functor to the integers, but you also have one to dynam, and I'm wondering many, I guess. I'm wondering if knowing the additive invariance tells you anything about the dynamics.
Not that we know of, but that is a great question, something to investigate. And I think this gets back to sort of let me pop that back to that slide. So this question of like, is it biologically relevant? That sort of thing might help you, if there's some relationship between them, understand what sort of invariants are, or what sort of constraints on invariants are biologically relevant, if we can connect them to how the dynamical system behaves.
If the additive invariants bound the degree of polynomials in the mass action,
Like your additive invariants, that there are ones that say you have no transitions with more than 3 inputs. that, right, if all the invariants that correspond to the like 3 input and k output transitions, if those are all 0, then you know that there are only quadratic terms in the mass action. So there's already like, if this invariant has this value, then the dynamics satisfies this property. But I think turning that into a statement of the trajectories is super hard.
Thanks, James.
What about typed Petri nets?
Typed Petri nets. I think those are great. So something that I was thinking about is like,
I agree, Sophie.
like I was thinking, maybe I want an atom invariant that not just says like counts the number of catalysts, but counts the number of like iron catalysts or something like that. And this seems totally plausible to extend this to the idea. And for that, you need a type Petri net because you want to say, these species are of type iron or something, and these species are not. It seems totally plausible to extend this to the idea of typed Petri nets.
Awesome.
The classic have you tried
Any other questions here?
We're fine with that.
Oh, thank you.
Yeah. I guess I can read it.
Could you read it out? Could you read it out?
What about just additive set valued invariants, which give you invariants by composing with cardinality? So for every, so I guess you're thinking, Jorge, for every open Petri net, you get a set of something?
Yeah.
Go
So
ahead.
set valued ones that the ones you are considering factor through sets, in fact.
So these added invariants in fact factor through sets is the conjecture?
Maybe this gives you more some other invariants.
Mm-hmm. Yeah, that sounds really interesting. I'm not
sub-additive instead of additive, or you take how do you call that, disjoint unions or direct union.
Mm-hmm. Yeah, that sounds really interesting. It seems like there's a lot of interest in more additive invariants with different codomains. So that sounds like good work.
Mm-hmm. Hey, thank you.
Thank you.
Is in the context of Petri nets, is there any reason to be interested in, for a given Petri net, the behavior of the n-fold product of that Petri net, or maybe as n goes to infinity, the asymptotic behavior of that?
Interesting. My gut says that if I like the n-fold behavior of it, I think because they're all independent, right? You should be able to analyze them independently and then add sort of the results together. Or in the case of like, if you're turning them to ODEs, you really just get n distinct ODEs that all look exactly the same.
Mm-hmm.
So I'm not sure. I'm
that
sure.
Doesn't seem particularly interesting.
Yeah. Although one thing you can do then is to then sort of compose those and see what happens. That seems sort of interesting. If you have multiple processes that are then interacting in multiple identical processes that are then interacting in some way.
I see. I mean, the reason for my question is that in the context of resource theories, the additive monotones are the ones that classify the asymptotic behavior or the asymptotic conversion relations. And so I was wondering if the additive invariants here kind of tell you something about how the behavior of these not clear.
Interesting. Yeah, I'm not sure.
Thanks.
Any other questions?
So I'm just curious, you mentioned that in MOPE nets, when you compose them, it can't create a catalyst in the sense of a single step catalyst. But you can also have catalytic reactions with multiple steps, like in Michaelis-Menten kinetics, where there's one reaction where the substrate binds to the enzyme in another reaction where the product unbinds. I'm wondering whether, if you know, whether MOPE nets also prevent the formation of that type of catalyst.
Sorry, let me just make sure I understand what you're saying. So a multiple, how does it work? So it's like you have a species that's like the input to one transition and the output to of another?
Yeah, so
Somehow-
you should have two species going into this. There's two transitions.
Uh-huh.
Yeah, exactly. So that one's the catalyst, and then the first transition should have the substrate going into it, and then the second one. Wait, am I confusing myself? Yeah, that looks right.
This?
Yeah. Yeah, that's right. So yeah, the middle species is the kind of bound catalyst.
Okay, and so we consider this the catalyst?
That's like the catalyst. That's like the catalyst with something bound onto it, and then the one at the top is the catalyst without anything bound to it.
Okay, and the question is, can you?
Yeah, the question is, yeah, exactly.
So this sort of thing can you can sort of these could if I look at the top one, for example, it could be separate in the two components and then glue it together afterwards.
Okay.
It's really just relationships between a single transition and its species.
Okay, thanks very much.
Okay, wonderful. Thank you, Sophie. Let's thank our speaker again.